Hello everybody. In this video, I'm going to discuss converting common fractions to decimals and converting decimals to common fractions. The first part of this is easy. The second part can be a challenge. We're going to do a little prime factoring and simplification of fractions. If you are a little rusty on this, you might want to review the following videos. Video number 7 on prime numbers, video number 8 on powers and roots, video number 9 on least common multiple and greatest common factor. In this video, we're going to be using the greatest common factor. Video number 10, Introduction to Fractions. I am going to take advantage of a concept I brought up on the last video, video number 15, Multiplication and Division of Decimals. In that video, I discussed the relationship between division and fractions. When we first learned division in grade school, most of us learned using this symbol. For instance, this is how we would express the operation of 5 divided by 8. For those of you who are trivia addicts, this symbol is called the obelisk. I have successfully lived my life without knowing this until a few minutes ago, so I wouldn't spend a lot of time and effort committing it to memory. A division problem is equivalent to a fraction, so we can alternatively write 5 divided by 8 in fractional form. All branches of mathematics outside of arithmetic use this notation rather than the obelisk. I can easily express the common fraction 5 over 8 as a decimal by treating it as a division problem and doing some old-fashioned long division. Let's try it. First, set up the long division problem. 8 doesn't go into 5, so put a 0 in the ones place and add a decimal point and a 0 in the tenths place. 8 goes into 56 times. Put the 6 in the quotient. Don't forget the decimal point. 6 times 8 is 48. 50 minus 48 is 2. Bring down a 0. 8 goes into 20 2 times. 2 times 8 is 16. 20 minus 16 is 4. Bring down another 0. 8 goes into 40 5 times. 5 times 8 is 40. 40 minus 40 is 0. We're done. The answer is 0.625. That's pretty straightforward. Converting 0.625 back into a fraction is a little uglier, but we can handle it. Remember from video number 14, Introduction to Decimals, that the first place to the right of the decimal point is the tenth place, the second is the hundredths place, and the third is the thousandth place. So the decimal 0.625 is equivalent to the fraction 625 over 1,000. Now our job is to reduce that fraction into simplest terms using prime factoring. I'll prime factor this very quickly for you. If you need to refresh yourself on the process, look at videos 7 through 10. The prime factor for 625 is 5 to the 4th power. The prime factors of 1,000 are 2 cubed times 5 cubed. The greatest common factor is 5 cubed, which we factor out from both the numerator and denominator. The fraction simplifies to 5 over 2 cubed, which is equal to 5 over 8. So far, so good. 0.625 is an example of a terminating decimal. That means that when we do the long division to convert the fraction of 5/8 into a decimal, we reach a point where we don't have to go any further. We can add more decimal places to a terminating decimal, but they will all be populated with zeros. The fraction we choose doesn't have to be a common fraction. What is 0.21 divided by 0.3? As I discussed in video number 15, Multiplication and Division of Decimals, my recommendation is to first convert the denominator into an integer. We do this by moving the decimal point one place to the right. That is equivalent to multiplying the denominator by 10. In order to maintain our equality, we have to move the decimal place on the numerator one place over to the right as well. Our problem is now 2.1 divided by 3. Use long division again and make sure to keep track of the decimal point. 3 does not go into 2, so put a 0 in the ones place. Then add the decimal point. 3 goes into 21 7 times. 7 times 3 is 21. 21 minus 21 is 0. We are done. The answer is 0.7. This solution is a terminating decimal. Now let's convert the fraction 1/3 to a decimal. Again, we do the long division. 3 goes into 1 0 times. Put in a decimal point and add a 0. 3 goes into 10 3 times. 3 times 3 is 9. 10 minus 9 is 1. Add a 0. 3 goes into 10 3 times. 3 times 3 is 9. 10 minus 9 is 1. In this case, we find ourselves in a long division loop which goes on forever. 1/3 in decimal is 0.3333 for as long as I desire to write down threes. I will be using the term ad infinitum, which is not exclusively a mathematical term, but indicates something that repeats forever or infinitely. Decimals that do not terminate, but rather have all or a portion of the decimal repeat itself ad infinitum, are called repeating decimals. There are a lot of examples of repeating decimals. The fraction 1/6 gives us the repeating decimal of 0.16666 with the 6 repeating ad infinitum. 1/12 gives us the repeating decimal 0.083333 with the 3 repeating ad infinitum. It is an important point that these decimals repeat, and therefore I can indicate the pattern of repetition. That portion of the decimal that repeats is called the repetend, or reptend. This is also a term I didn't know until a few minutes ago, but I like the way it sounds. When I want to express these decimals precisely, I put a line over the reptend, that is, the portion of the decimal that repeats. The decimal equivalent of 4/11 is 0.363636 ad infinitum. So I would express this as 0.36 with a line over the 3 and 6 to indicate that those two numbers are the reptend. As I mentioned earlier, the decimal equivalent of 1/6 is 0.1666 ad infinitum. We would indicate that repetition by putting a line over the 6, since that is the portion of the decimal that repeats. The decimal equivalent of the fraction 5/7 is 0.714285, with those 6 numbers repeating ad infinitum. Therefore, the decimal would be represented with a line over those 6 numbers. The problem comes in when I try to convert a repeating decimal back to the common fraction. Specifically, the problem is that, while I can express the decimal precisely by indicating the pattern of repetition, in order to work with a repeating decimal, I must decide exactly how many decimal places I want to write, and wherever I stop, I have introduced a tiny inaccuracy in my expression of that decimal. That tiny inaccuracy is enough to create problems. Let's try it for 1/3 equals 0.333 ad infinitum. In order to use this decimal in any useful application, I have to truncate the string of 3's at some point. Suppose I decide to truncate this decimal at the first 2 decimal places, that is, taking the decimal out to the hundredths place. Then the fraction is 33/100. As it is written, 33/100 is in its simplest form. But we know that the original fraction was 1/3, not 33/100. I'm stuck. If I go out to 3 decimal places, it doesn't help. Now my fraction is 333/1000. Again, this is the simplest form of that fraction, but also again, it is not equal to the original fraction of 1/3. Close, but no cigar, as they say. This problem is probably okay for simple repeating decimals like 0.333 or 0.1666, where we can simply memorize the decimal equivalents of the fractions 1/3 or 1/6. But it can quickly become unworkable with other decimals. Take this one, for example, 0.153846 153846 153846. If you study it long enough, you can see the repeating pattern. I'll express it using the proper notation as follows. Now let's try to convert this back to its original fraction. The decimal repeats every 6 decimal places, so if I take the first full repetition, the 6th decimal place is the 1/millionth place. So my fraction is 153,846/1,000,000. The prime factorization of the numerator, 153,846, is 2 times 3 cubed times 7 times 11 times 37. Believe me, it was quite a bit of work to find that factorization. The prime factorization of 1 million is 2 to the 6th power times 5 to the 6th power. We can factor out a 2 from the numerator and the denominator and multiply my prime numbers out again, but we are left with 76,923 over 500,000. So that fraction is in its simplest form. It would be virtually impossible to figure out that the original fraction is simply 2 over 13. Factoring this decimal was an ugly process that ultimately led us nowhere. It simply taught us that once you convert a fraction to a repeating decimal, there is no practical way of converting it back to the same fraction again.
Hello, darling.
Is this the Decimal Diva again?
Of course, darling.
Well, this is a great deal more sedate than the music you played last time.
Yes, it's just a little something that Ludwig penned for me years ago.
This is Für Elise. Are you telling me that Ludwig van Beethoven wrote this for you?
Well, what do you know about Für Elise?
I know that the title means For Elise, and the music score was discovered about 40 years after Beethoven's death, and no one is certain who Elise was, or even if Elise was her real name.
Well, that's not quite true, is it, darling? I know exactly who Beethoven wrote this for.
You're not serious.
Oh, darling, I believe you're jealous. I simply adore that about you.
I'm not jealous.
I love it when your ears turn red.
Please, let me get back to this seminar.
Toodaloo, darling.
Yes, toodaloo. Excuse me, everybody. Please give me a moment for my ears to return to normal color. All right, I'm ready to go. We have one final point to cover in this video. You might recall from video number 2, different number types, that real numbers, the numbers that apply to our physical world, are made up broadly of one of two different number types, rational numbers and irrational numbers. The term rational number is derived from the term ratio, which is another term for fraction. All rational numbers can be expressed as the ratio of two integers, that is, as common fractions. From the standpoint of decimals, all rational numbers can be written as decimals that either terminate or repeat. Some of these reptends can get to be quite long. The reptend for 1 over 17 is 05882352941176647. The reptend for 1 over 97 is 96 digits long. But regardless of how ugly the reptend is, all rational numbers eventually either terminate or repeat. Irrational numbers are numbers that cannot be written as common fractions. There are an infinite number of irrational numbers, but from a practical standpoint, we only deal with a relatively small number of them. Still, those few tend to pop up often. Pi is the most widely recognized irrational number. If we have a circle with a diameter of 1 foot, then the circumference of that circle, that is, the distance an ant would travel in going around the circle, is an irrational number. Since we can't express that distance as a fraction, we use a Greek letter, in this case, the Greek letter pi. When we try to express an irrational number as a decimal, we find that the decimal neither terminates nor repeats. Pi has been calculated to about 50 trillion digits without terminating or repeating, and it never will terminate or repeat. If you have a square with a length of 1 foot on each side, and an ant crawled from one corner straight to the diagonally opposite corner, then the distance that ant travels is an irrational number. It is the square root of 2. The value of the square root of 2 has been calculated to more than 10 million decimal places, and of course also does not terminate or repeat. Irrational numbers tend to bother a lot of people, in fact, probably most people. There is a reason that we call illogical actions or people irrational. Irrational numbers are a problem if we try to express them as common fractions, but they are relatively easy to work with as decimals. We can't express them precisely as decimals, nor can we indicate a pattern of repetition since one does not exist, but I can use decimals to express irrational numbers to whatever level of precision I require. So from a practical standpoint, irrational numbers are not particularly difficult to work with. We are done with this video. In the next video, I would like to talk about how the inexact expression of a repeating decimal, or an irrational number expressed as a decimal, can lead to something called an iterative error, and how we can best avoid this type of error. This topic is really an offshoot of a larger topic of precision and accuracy, so I think I will expand the discussion to include other aspects of this topic. Have a good day, everybody.
We hope to see you at Veterans Upward Bound very soon, and recommend a friend.